Okay, hi, I'm Edwin,
Hi, I'm Mark.
and today we're going to be talking about universal gravitation. Isaac Newton compared the acceleration of the moon to the acceleration of objects on Earth. Believing that the gravitation forces were responsible for each, Newton was able to draw an important conclusion about the dependence of the gravity upon distance. This comparison led him to conclude that the force of gravitational attraction between the Earth and other objects is inversely proportional to the distance separating the Earth's center from the object's center. But distance is not the only variable affecting the magnitude of a gravitational force. Consider Newton's famous equation that we have right here. We have F net equal mass times acceleration.
Newton knew that the force that caused the apple's acceleration, gravity, must be dependent upon the mass of the apple. And since the force acting to cause the apple's downward acceleration also causes the Earth's upward acceleration, Newton's third law, that force must also depend upon the mass of the Earth. So for Newton, the force of gravity acting between the Earth and any other object is directly proportional to the mass of the Earth, directly proportional to the mass of the object, and inversely proportional to the square of the distance that separates the centers of the Earth and the object.
But Newton's law of universal gravitation extends gravity beyond Earth. Newton's law of universal gravitation is about the universality of gravity. Newton's place in the Gravity Hall of Fame is not due to his discovery of gravity, but rather due to his discovery that gravitation is universal. All objects attract each other with force of gravitational attraction. Gravity is universal. This force of gravitation attraction is directly dependent upon the masses of both objects and inversely proportional to the square of the distance that separates their centers. Newton's conclusions about the magnitude of gravitational forces is summarized symbolically as here in this equation that we have.
So here in the equation, F equals mass 1 plus mass 2 all over r squared. F is the force of gravitation between the two objects. Mass 1 is the mass of the first object. Mass 2 is the mass of the second object. And r is the distance between the objects, which is squared in the equation.
Since the gravitational force is directly proportional to the mass of interacting objects, more massive objects will attract each other with a greater gravitational force. So as the mass of either object is increased, the force of gravitational attraction between them also increase. And the mass of one object is doubled, then the force of gravity between them is doubled. If the mass of one of the object is tripled, then the force of gravity between them is tripled. If the mass of both of the object is doubled, then the force of gravity between them is quadrupled, and so on. Okay. So here we're going to have the effect of mass on F. Alright.
So here, for example, on this right side where the black is at, shows the effect of distance between two objects. If the distance is doubled between two objects, the force between them would be 1/4. And here, on the left side, on the red, shows the effect of mass on the force of gravity. If you see on the top, everything's normal with the coefficient of 1. But on the bottom, if you double the mass of one of the objects and keep the same distance, the force of gravity will still be the same. The end.